Okay, our next item of discussion is going to be the same thing, but this time we will focus on how to measure these. Because, yeah, I can talk about all of these phase relationships, but if I don't give you practical ways of determining some of these numbers, because you need only some of them, then you can determine the rest from analytical calculations like these. But you need something, you need some data from a given soil that you are going to study. So for that, we do lab experiments. So in this lecture, I'm going to focus on the lab experiments that are related to determining the physical properties and phase relationships. So the first one, the simplest one, is determination of water content. So let's remember what water content was. Water content is mass of water divided by mass of solids. Okay, so what you do is this. You take a soil sample or specimen. So first step, you weigh the soil. What do you get? Okay, when you weigh, you get the weight, but also you get the mass. So you get total mass, which is mass of solids plus mass of water. Then you need a way to separate this solids and water, physically separate them so that you can determine individual weights. So what is the easiest way of removing water? You can dry it. So the next step is dry the soil. And you can't just leave it open in the air to dry, because then it won't dry completely. There is humidity in the air. It is going to come to a balance of humidity, but it won't be absolutely dry. You can't throw it into a pizza oven or something like that, because then you might burn you might cause some chemical changes. If you have some organics, you might burn them, etc. So the standard way of doing this is dry the soil in a 110 degrees Celsius oven for a day. So it's not a very hot oven, but you keep your soil for a long time in it. There is also ways of doing this in a microwave, but I don't like it. I don't recommend it, because sometimes entrapped gas pockets in your soil blow up, and it's not a matter of safety, but it scatters pieces of soil around into the microwave and disrupts the measurements. So it is better to use a conventional oven set to 110 degrees. Then cool the sample down in a desiccator. The reason we have this step is because if you try to determine the mass of a warm object, because the warm object will cause convection currents, it's going to affect the mass measurements. So we want to weigh our masses in, or weights in, room temperature basically, or in the same temperature as the room. So then weigh the dry soil, which is what? It is mass of solids. And once you do that, you can directly write this. Total mass minus mass of solids will get you mass of water. Divide that by mass of solids, you get water content. Of course, there are further practical details here, because you are not going to put the soil into the oven or into the microwave or into the desiccator jar just as bare soil. It will have to have a container, and then you need to remember to measure the mass of the container and subtract it from your measurements, etc. So, but anyway, that is just very simple physics. So you can figure that out in the lab sessions. So this is the most basic measurement we have in the soil laboratory. Now, the next measurement is bulk density. So, the bulk density or unit weight, since one is gravity times or divided by the other, they are interchangeable. So here let's use density so that I don't have to write G all over the place. So my bulk density is total mass divided by total volume. And the total mass is very simple. I can just weigh my soil. Now, total volume might not be that straightforward. So here I'm going to separate it into two. If it is a regularly shaped object, regular shape, such as a cylinder or a cube of soil or rectangular prism, you determine by geometry. So then you can determine by measuring dimensions and calculate by geometry. Calculating by geometry. But here there is a little note. Multiple measurements are better. Multiple measurements to ensure it is actually a regular geometry. So it might look like a cylinder to you, but maybe it is a little fatter at the middle and smaller on the top and bottom. So if you just measure it from the middle, you get the incorrect dimension or incorrect volume. So it is better to take multiple measurements for the same dimension. So if you are measuring diameter, measure it in different angles at different locations. If you are determining height of the cylinder, again, maybe its top and bottom faces are not parallel. So if they are not parallel, you need to make at least 2 measurements to get their average. So you might need multiple measurements. The more complicated case is an irregular geometry. Now, if you have an irregularly shaped object, like imagine a lump of soil, the most practical way is if you submerge it into a liquid. Now, then what? Then you can the liquid, because the difference is buoyancy force, and that will be volume of objects times density of, or unit weight of, let's write unit weight because I said force, unit weight of liquid. So that sounds straightforward. Just throw your soil into water. No, that doesn't work because soil is porous. Therefore, liquid can enter the pores. So there are a couple of ways to avoid that. One way is if your liquid is mercury, and if you force it down into the mercury, because mercury, it will float in mercury, because mercury has a very high surface tension, it doesn't go into the pores. But mercury is poisonous and we don't use that. So instead we use water, but we coat the soil with something impermeable and something easy to use, such as wax. So you melt wax, you dip your soil into wax, and then you take it out, and now you have an impermeable coating. But then you have disrupted the measurements, because now your object is weight of soil, volume of soil plus volume of wax. But you can also determine the mass of that object, and it will be total mass which you already have determined plus mass of wax. So you know this one, you can figure out mass of wax. So then you can directly say volume of wax is going to be mass of wax divided by density of wax, because wax is a known chemical substance, so its density is also, you can look it up from a chemistry book or something. So you can determine the volume of wax and subtract it. Of course, once again, you might need to figure out the practical details. For example, how are you going to weigh the soil inside water? Usually what you do is you can have it in a little suspended tray and then have it suspended by a hanger and dip that soil and hanger into a container of water. But then again, you are adding the volume of that tray, that container. So you need to also do the same thing without the soil to figure out the volume of that container as well. So anyway, you can once again figure that kind of things when you do this in the lab. But not our lectures lab. We aren't doing that. In this lecture we are just dealing with regularly shaped determinations in the lab. So the last one is determination of specific gravity of solids. Now let's figure this out. Specific gravity of solids is mass of solids divided by volume of solids times 1 over density of, sorry, not solids, water. Because this is, remember, density of solids divided by density of water. So, okay, I know density of water, so that's not a problem. Once again, it is mass of solids, which I can determine. So I can, once again, I can weigh this. So once again, all I need to do is determine this volume of solids. And this time it is an irregularly shaped object, or a plentitude of irregularly shaped objects. And this time, actually, I have it a little bit easier than the bulk density because this time I actually want to determine only the solids volume, which means I want my liquid, I want my water to get into the pores, which it will want to do. So let's again submerge. But this time there is a problem with that as well. When you take a lump of soil and throw it in water, the water isn't directly occupy all the voids. The reason for that is because there is air in there, and when you suddenly surround that void space with water, air doesn't have any place, any way to go out. And it doesn't just float out in bubbles because the pores are small, and due to surface tension, the air will be trapped inside. So you submerge and then apply vacuum. So when you apply vacuum, the air pockets, the entrapped air will expand in volume greatly, and once it does that, it will break apart the soil skeleton. It will just be free and it will float up in the water. So the way this is commonly done is you get a volumetric bottle. There are different kinds of bottles, flasks, iodine flask, etc. But I'm just going to call it a flask. But the property of this flask has to be that you can repeatably fill it always to the same level. So if it is like this, you can always fill it to this level. So when I do this and you do this, it is exactly the same. So the most primitive versions have just a line here, and by your eyesight you just adjust it to that level. More advanced ones have a cap here that basically that fits in there, and it also has a tiny tube outlets getting out of there, so any excess water will just flow out, and it has a sharp edge, so you can very sensitively fill it to the same level. Or the iodine flask version has again this cap that is able to perfectly fit without entrapping any air there. So there are different ways, but the essential information is that can be filled to exactly the same volume repeatably. So in our lab we have these and these. You might see those if you do a lab session on this. So then what? Then what you do is you need to weigh the flask. Mass of flask. Then weigh the flask filled with water. By the way, there are again practical details, like even if you are filling it with just water, not soil, in order not to have any air bubbles sticking to the surface, you have to vacuum it. Flask plus water. Then of course weigh the soil as well, the dry soil, or you can weigh the moist soil. If you also have a water content measurement, you can figure it out from phase relations. So this is mass of solids. So the soil into the flask and vacuum, as I mentioned earlier. Then weigh. Now what do we get from there? Let's call it and flask plus water plus soil. So what do we have now? Now we have in our hands we have a mass of solids. We also determined mass of flask plus water. And if I subtract mass of flask plus water plus solid measurement, then what do you get? Is that zero? Do you think it's zero? No, it's not. It's not zero. The reason for that is because this flask plus water, this water is more water. It is the entire volume of the flask, whereas this is less water. How much less? By exactly the volume of solids, because the volume of solids are no longer occupied by water. So this water is less than that water. That's why this difference gets you the volume of that solid times density of water. And look what we have here. Volume of solid times density of water. So I directly obtained this entire denominator here. So there's a tiny extra baggage here that you need to consider, and that baggage is the specific gravity of solids is standardized at 20 degrees Celsius. So this density of water is at 20 degrees Celsius. So this is for soil mechanics purposes, maybe for purely scientific purposes it might be zero or something like that. I'm not sure about that, but for soil mechanics purposes we standardize it for 20 degrees, so that when somebody measures specific gravity in their lab and somebody else measures another in another lab and they have different temperatures, they still can calculate the same specific gravity. But this is at the lab temperature because you made the experiment at the temperature of the lab, or more precisely at the temperature of the water in your lab. So of course this is distilled water, by the way. So I need to also once I did this, I need to convert it into 20 degrees Celsius by multiplying it with a proportion of density at 20 degrees Celsius to density of water at the lab temperature, and you can get very precise density values at different temperatures for water anyway. You can find them in textbooks. So what you need to do then is convert this into convert this into what you want so that you can use it up there. Okay, so this concludes this section of the first chapter, but the first chapter has many more topics. So see you in the next lecture.